Welcome to this session of Shadow the Scientist. My name is Jamika Marshall, and I'm very pleased to serve as the Shadow the Scientist Programs Manager.
Exposure complete.
So Shadow the Scientist is brought to you, oops, sorry, let me share the wrong screen. Shadow the Scientist is brought to you by an amazing team of people at the University of California at Santa Cruz. Now, for our session tonight, you are in for an amazing treat. Not only will we have members of the Next Generation Virgo Cluster Survey team with us, but we also will have with us the founder of Shadow the Scientist and the faculty sponsor, Raja GuhaThakurta. He is going to be leading this session tonight and is right here ready to get going. And you can already hear that, you can hear the sounds from the computer talking about exposures being complete. So they are in the throes of their observations. Raja, how's it going?
It's going very well. Thanks, Jamika. I know it's been a very long day for you because this is what your third Shadow the Scientist session in a 24-hour period. Wow. What were the other two on?
Cryo-electron microscopy.
Wow. Both of them?
Yes.
Wow.
Both of them. Yeah.
So Aishani and Zayden, welcome. Zayden, we have, of course, spoken. You're a UCSC undergrad. Thanks, Jamika, for making me host. Okay.
Yes.
And
okay.
I can, since
I'm gonna log out.
Thank you, Jamika. Okay.
Have a good evening. Thank you, Zayden and Aishani.
Thank you so much.
Okay. Zayden, you're a second year undergrad?
First year.
First year undergrad at UCSC. Okay. And how about you, Aishani? Where are you connecting from? Aishani, where are you connecting from, Aishani? Are you able to unmute? Oh, now you should be able to. Okay, you should be able to unmute now. But if your mic is not working, you're welcome to type things into the chat. And Mincheng, welcome. Welcome back. Mincheng is part of our observing team. Aishani, how did you find out about Shadow the Scientist? Modern High School for Girls. Oh, fantastic. Which grade are you in? Or which class?
Hello, can you hear me?
Yeah, Mincheng, I can hear you.
Yeah, so now my name is Mincheng and I'm from the Peking University. Now it's 5 years graduated.
Excellent. And Aishani, I've visited your school many times. My sister, my sister's daughter, and various members of our family have attended that school, so I'm quite familiar with it.
Oh, yes, great.
Welcome back.
Okay.
Hello. Where's the big crowd tonight?
I know. Yesterday there was a huge crowd in person with Jamika.
Yeah. Sounded like they were going to be back tonight, but I guess not.
No, they were there in person, and that only happens once a month. Jamika goes up to the. It's quite a hike to the summit, and she lives in Hilo, so it's a long way back, driving late at night. So she does that once a month. But it was very effective. She said about 70 people came through in person while she was at the visitor center at Manakeh.
That's amazing.
I'm going to go ahead and share my screen. I know we'll have a couple of others from the science team joining us in a few minutes. Mincheng has joined already from Peking University. But let me share my screen real quick. And share with sound. So we are
DCD readout complete.
Continuing the same experiment that we started in February. And tonight's our fourth night in the month of May. our fourth half night in the month of May, and we had 2 half nights in the month of February. And because of the way the Earth rotates around the sun, we were allocated, in anticipation of the way the Earth rotates around the sun, we were allocated second half nights in February, so from midnight to sunrise, and first half nights in May. Turns out that galaxies that are up during the second half of the night in February are up during the first half of the night in May because of the way the Earth goes around the sun. So this was the people who schedule the telescope. I used to be a scheduler of this telescope for the folks who applied through the University of California time allocation committees. So these are the sorts of things you have to think about. So we are taking a very long exposure on the blue side, about 10 minutes. Exposure time is 600 seconds, not 15. We're using a script. That's why it shows up in parentheses. If we weren't using the script and running things manually, we would type into this window. But what's in parentheses, the script overwrites what's in the manual box. So on the blue side, we're running a 10-minute exposure. Sorry, on the red side, I believe we're running multiple, 374. So just under 3 minutes per exposure. And the red side has horrible cosmic ray. Let's look at this really long one. Ashani, have you been part of Shadow the Scientist before? Oh, in class 8 once. Wow, a couple of years ago then. Wow. What subject are you interested in studying in I guess in 11 and in grades 11 and 12? Would it be science or something else? Physics, chemistry, and math. Okay, thanks. There are actually a lot of all three of those things.
Exposure
Oh, that's Rita.
complete.
There's a lot of physics, chemistry, and math that goes into the study of stars. Hey, Rita. Hey, Rita.
Hey. Figured I'd sign in for a few minutes.
Thank you. Rita, please, since you're here only for a few minutes, please introduce yourself to the group.
Right. So I'm tonight's telescope operator. I'm actually at the summit.
DCD readout complete.
Sorry for the background noise. There's like 3
No.
Zooms going on, but
No, I'm deliberately sharing my screen with sound so that people can hear what's
Okay.
going on with the experiment. Sorry
Yeah.
about
So we're just up here observing tonight, and I'm helping you guys take hopefully really good data tonight.
that. Rita, where were you before you came to Keck?
So I was at Subaru for about 9 years, and then I've been here now for like 4 years, which is longer than it seems.
Have you always lived on the Big Island, or were you in a different location before Subaru?
I'm originally from Portland, Oregon.
I see.
I went to school at U of A in Arizona, down in Tucson though.
That's an amazing school. It's a very, very good school. Did you study astro there?
I did astronomy and physics as an undergrad, and then later I actually went back and got a master's degree in optical sciences.
That's a great school for optical sciences. One of the best schools in the world.
Yeah, I picked it well.
Well, thank you for helping us out tonight.
Yeah, of course.
So we have Aishani, who is a high school student at a school called Modern High School for Girls in Kolkata in India. So it is the middle of the afternoon for her, 1:45. Min Cheng is connected from Peking University. in China. He's a member of our science team, actually. Just joining Eric's group. And it is, what, 3:30 in the afternoon, 3:15 in the afternoon for him. Zayden is one of my undergraduate research students at UC Santa Cruz. So it's very late at night for him. We're just starting to work on the M32 galaxy. And Jim is joining us from Southern California and was, has been a Shadow the Scientist regular from a session we did at Griffith Observatory in SoCal years ago. So thanks, Rita. We've been so, fingers crossed, we've been so fortunate with the weather.
Yeah, I cannot take credit for that, but you guys picked a couple of good nights.
We did have a question about, in the magic buoy,
Exposure complete.
we were getting a very high value for seeing almost 2 arc seconds when we did the full width half maximum. Is that because the guide star is faint, or it's a galaxy?
Yeah, it's probably because the guide star is faint. And looking at this particular one, it's
Exposure
probably also a
complete.
galaxy. It looks a little bit elongated to me. So
Gotcha.
hold on 1 second, we gotta move.
No problem. So folks on Zoom, what Rita and our science team are doing, they just applied this thing over here. If you can see my cursor right there, says EN 36.18 minus 91.6. EN literally
DCD
stands for
readout complete.
east and north. Should offset the telescope
DCD readout
east and
complete.
north. And since the north offset was negative, it actually moved it east and south. And to go from the offset location to the location of our science target, we are, as we did the last few nights, what we're doing is we're looking at a very faint galaxy, and we're looking just off the very faint galaxy and taking a difference. Oh, there's Eric. Eric has joined as well. Great.
So if you look back at the magic guider now, the full width half max dropped to about 1 arc second.
Oh, wow.
We've got a slightly different guide star, right? Because we're bouncing between 2 of them.
Oh, gotcha.
And this one is probably a star rather than a galaxy.
So that would be in the magic window here. Okay. Eric, Rita was just saying that the object she was guiding on before was probably a galaxy, and that's why we were getting such high FWHM full width half maximum.
Yeah, it was like almost 2 arc seconds.
Now it's apparently 1 if you click on FWHM here.
So the guider will always show a full width half max that's a little higher than it really is being seen in the instrument. And especially if I guide on something that's not a star.
Yeah, and there's the drop right there from 2 to 1.
Yeah, I just joined, guys, because hearing it on there, I was like, oh, right. Okay.
So Eric, Ming Cheng is here, and you can probably see, I just wanted to, you met Jim before, but Zayden is one of my just started working with me as an undergrad at UCSC. He's a freshman at UCSC. Zayden's gonna look at integrated light spectra of M32 with Deimos. So we did a multi-slit observation of stars around Deimos, but some slits landed so close to M32's nucleus that you can actually measure the integrated light. And so we're going to do non-local sky subtraction and extract velocity and velocity dispersion, part of an effort to do kinematical modeling of that galaxy. You met Jim, but Ashani is a 10th grade student in a school called Modern High School for Girls in Kolkata, India. It's a school with which I've had a very long partnership. My sister went to that school. My sister's daughter went to the school. We have several family members who went to the school. And so I've actually been visiting them since, I don't know, long time. from over 15 years. When we've done shadow sessions. They've been part of shadow sessions, have done lectures. They've actually even been part of SIP, but virtually. We haven't had students come here from Modern High School.
Great.
So the flux level also went up for the star, right? When the counts went up, huh?
Yeah, we got a better guide star on this one.
Okay. The guiding is not super crucial for these observations, but I mean, we do have some point sources in here, so.
Now,
As long as we can find the center of the whatever it is, then guiding is fine.
Yeah, okay.
what is the thing that causes vignetting of the center of the magic field?
So that's the hole that we're actually sending light down to your
Oh, I
science
see.
instrument. So we've
Got
got an
it.
annular guider, and the center gets sent down optics basically straight to the instrument.
And those optics are out of focus. Is that why it's fuzzy like that, or?
I would have to look at the diagram to know for sure.
No
but
problem.
probably.
No worries.
I suspect yes.
Elisa and Sangsun have just joined. I'm going to stop sharing for a moment so that I can see people. So our whole science team is here. Elisa, Eric, Sangsun, Min Cheng, and me. So Jim has asked the great question: will the 6 nights of observing we've done this year get us enough data to do our analysis? If not, how much do you expect it to take? We'll know the answer after we analyze these data, and it'll all be, we think right now we're not limited by photon noise or boson noise in the counts, but rather by systematics, how well we can subtract the night sky, the blank sky, from the Sky Plus galaxy. Lisa's been working very hard on this. I'm going to go visit her and maybe spend a day looking at this. So time will tell. But it's one of those things where if we don't get this, if we don't get anything in 6 nights, we have to worry about a point of diminishing returns. And say that, look, these sorts of galaxies can only be tackled when bigger telescopes and more powerful spectrographs come online. I don't know if we're at that point yet, but you can imagine that
TCD readout.
spending
complete.
3 full nights on something and still not being able to get anything would be, would be something that could send us to that conclusion.
That makes sense.
Yeah, I think if we don't if we don't see anything after all these observations, then it's just not going to be possible, at least using the current techniques and instruments. But it would be, if we do see something and it's not quite enough, then we could maybe think about proposing to get more observations, but we'll see.
So
What
right
did-
now, this is all you have scheduled on this.
Yes, that's right. This is actually our last
Right.
our last observations for this program, and we did pretty well this semester, knock on wood. The weather's been good to us. Unlike
Of averages, because when we started this program, we had really bad weather.
yeah.
I was going to say, it's not going to be all or nothing, because the patch of sky we're looking at, most of it is diffuse light from this very faint galaxy, but there are a few spots, bright spots, figuratively and literally bright spots. Those they could either be star clusters orbiting this galaxy of interest, or they could be background galaxies. And either way, our hope is to be able to tell one from the other. If it's a background galaxy, it's not much of scientific interest, but if it's a star cluster, there's a very good chance we'll be able to measure the velocity of the star cluster. And there's like a handful of such objects, right? Elisa and Eric and Sungsoon, is it 3 objects like that in the field of view or 5?
There are like 7
Okay.
objects.
But not all of them are necessarily globular clusters, right?
I don't think all of them, at
Okay.
least 2 2 I think they are. The others I haven't checked with them with the catalog. Yeah.
But for this galaxy, using a different instrument on Keck called DEIMOS, we have velocities for a few globular clusters, right? 3, is it so far?
For this galaxy, it must be something like 6, I think.
6, okay. So we might be able to get a velocity dispersion just from the star clusters. That is, how fast are the star clusters moving around the galaxy as opposed to individual stars? Ideally, we measure both. How fast are the star clusters moving around? There, the bottleneck is we have only a handful of star clusters. So there's a different kind of noise that enters, which is counting statistics in the number of how well can you measure the width of a bell curve from just sampling it in 6 places. That's the bottleneck with using star clusters versus that while there are many, many stars that make up the galaxy, they're so faint that our limitation is the number of photons we're collecting that makes it difficult to measure. So we're sort of hoping to get at both of these difficult measurements.
So this is the first time anyone's tried to do this with one of these objects, right?
With
one of these
this
CUH.
particular one, first time, I believe, right?
These
Peter-
kinds of observations have been made on similar types of objects, but all the ones that have been successful are typically, something like 5 times or even 10 times brighter than what we're looking at. And we actually do have a program as well to look at this galaxy, to look for more star clusters in this galaxy with JWST. So that's another way we're trying to tackle this problem. So
and this was a proposal you led, Eric, and one time on.
And Lisa, yes. Mm-hmm.
But this JWST proposals are oversubscribed by a factor of 10, something like that.
Mm-hmm.
That is, there's 10 times as many proposals as there's time to give out. So it's quite a win. So, and Sungsoon's on the proposal as well, right? I know.
Mm-hmm.
I'm on the proposal. Who else? Chris is on the proposal.
Yeah, Pat Durrell.
Both Pats, right?
GBS team. Yeah, a number of people from the NGBS team. So it reminds me that we have to get to finalizing our observation design so that they can schedule it. The next cycle for JWST, the observations start July 1st. So
wow.
But yeah, when you have an interesting problem like this, you kind of throw everything you have at it and see what you find.
And these will be spectra in the near infrared, right?
Mm-hmm.
What lines do you expect to get there?
DCD readout
Like
complete.
CO?
The CO, yeah, it's this
Bandhead.
CO bandheads.
In like red giants? Red giants, right? I guess.
Yeah, red giants. Yeah.
What wavelength is that at? Like 2 microns, 3 microns?
It's like 2 micron. I think it's 2 microns and a bit. Yeah, 2.1 or something.
Okay.
But we also get spectra into the. Oh, we made this calculation, Lisa, right? Whether we wanted. Were we going to get spectra in the J band as well? I can't remember if it's simultaneous, but
1.2 microns.
yeah. But the CO, yeah, the CO bandheads are the main features, and we're just getting velocities for the star clusters, so they're sharp features.
Mm-hmm. Well, that's the beautiful thing about something like James Webb. if you know the properties of the astrophysical object, you know exactly how much exposure time it takes to get what signal to noise, right? It's very predictable. There's no atmospheric blurring to worry about, anything like that. Do you have to first image and then design the microshutter array?
We have to take images first with GWST because we don't have images that go deep enough to do the selection from the ground. And also we don't, I mean, I think you need the coordinates to be precise enough to design the microshutter array. Yeah. And then once we get those images, I think they give us 60 days to design the spectroscopic configuration, and then they schedule that.
No.
Yeah, those are gonna be some fun 60 days, huh, Lisa?
That's
was gonna say that.
ridiculous.
Can
Huh?
we do science with the imaging, with the pre-imaging? Because you'll have beautiful like profiles of these globular clusters at JWST resolution.
Yeah, I mean, we could, there's definitely science we could do, although as we didn't include it in the proposal, but it doesn't mean we can't do it.
That means you
It
can
will
ask for
not be
archival
paid.
money to do it.
That's true.
No, but it should be deep enough to measure things like core radius and all that, right?
We could measure sizes, I think. I don't know if we could measure full king profiles. Yeah. But yeah, the observations are, I mean, there's a part of me that thought, oh, we should try to go deeper on the imaging to get individual RGB stars. Even though we wouldn't be doing spectroscopy, we could do individual RGB stars. But
Just to get the tip of the giant branch and things like that.
yeah, but I didn't want to muddy up the proposal by trying to do too much. Like, this is the way it was. Like, we have a clear science question. We're going to do the observations that address that question, and we're not going to add anything else. Isn't this one of the targets also that is part of Chris Mihos's Hubble program to do TRGB distances?
That is a very good question, and I should know it.
So to Aishani, Zayden, Jim, and Mincheng, as Eric said, these galaxies are so exotic, but also difficult to study. We're throwing some of the world's biggest, well, not some of the three most powerful telescopes in the world at this problem, right? The Hubble Space Telescope, James Webb, and Keck.
I'm sure this was mentioned in a previous shadow session that I seem to remember that it was mentioned, but I've forgotten the answer. How are these extremely dim objects discovered in the first place?
That's for Eric to answer and Sang-Soon to answer.
Yeah, well, yeah, Sang-Soon, do you want to go since you wrote the
paper? Can I display your paper?
Yeah.
Let me do that. Let me display.
So it's kind of we have some deep imaging survey using the CFHT telescope in Hawaii. That's close to the Keck. So with that observation, we have some.
Exposure complete.
Oh, sorry. Yeah. So we have very deep imaging, and then we made a galaxy catalog about these kind of images, and of course for that there's careful processing to get the faint light of these kind of galaxies. With the galaxy catalog, we try to estimate their properties, something like luminosity or surface brightness.
Complete.
With that, we categorize a little far from mainstream sequence of galaxies in certain scaling relations. These galaxies are a little far from the normal galaxy scaling relation. So that's what we found for these galaxies. Maybe Eric can add more.
Can you please send me a link to your paper if you have it handy? Otherwise, I can look for it.
This one is my iPad, so I think I cannot
Oh,
send
no
the
problem.
link.
I'll look for it.
Yeah, I think actually I still have it up from yesterday. I think I sent it to you yesterday. Of course, that chat doesn't
Yeah.
let me
Thank you.
I still have it here. Yeah, here it is. This is
Was that the link you posted yesterday? I still
I
have
think
that
it
up.
is.
Yeah.
And
Oh,
so
there it is. Okay.
the yeah, so the images that we use are from this wide field camera on the Canada-France Hawaii telescope, and we did the survey of the Virgo cluster, which is the nearest galaxy cluster, and it's really tricky to find these kinds of galaxies because they could look like just flares of light that reflect internal reflection. So the team, and not me, but others in the team did a lot of work looking for anything that could be a little wisp of something, and then they took properties, they measured the properties, they also looked at them all by eye to see if they look real, and so that's how you get the properties of these galaxies. So the luminosity, the sizes of them, and then their surface brightness, which is basically how much luminosity within a certain area. And so, as Sang-Soon mentioned, their galaxies don't just occupy, they're not like all different kinds of sizes and all different luminosities. There's a relation that governs where they are, like how more luminous galaxies tend to be larger, less luminous galaxies tend to be smaller. And these galaxies are ones that are outliers on the relation. So they tend to be, they're much larger for their luminosity, which also means that they're much sort of more diffuse. And so, it's not clear how, from our models of how galaxies form and in our simulations, like it's not clear how these galaxies form. So we're trying to explore their properties and get a better sense for what that tells us about galaxy evolution processes and also about dark matter, if there is dark matter in them.
So can you guys see the screen I'm sharing?
Yes.
So on the y-axis, just like Eric was saying, that there's a relationship that's illustrated in this panel, the right panel. Ignore the left and middle panels. You can think of the y-axis as how many stars a galaxy has. So galaxies at the top here have lots of stars. Galaxies at the bottom here have very few stars. So the y-axis is how many stars. And the x-axis is size, meaning the radius of the circle that contains half the stars of the galaxy, right? Effective radius. I think it's something related to that. So you can see a slight trend line, this curved line goes, every dot is a galaxy. Imagine that every tiny dot is a galaxy. So you can see that the more stars a galaxy has, the bigger it tends to be. This is measured in kiloparsecs, which is kiloparsec is 3,000, a little over 3,000 light years. So the galaxies with very few stars occupy a small amount of space. Galaxies with lots of stars occupy a large amount of space. But there are outliers in this relation. These things that are marked in red and blue, these are considered ultra-diffuse galaxies because given the number of stars they have, they are bigger than the typical galaxy with that number of stars. So if you look at, let's say, this red dot here, it's quite a bit bigger than other galaxies with comparable numbers of stars. This is a logarithmic scale. So when you take a step like this, that's a factor of 3. That's a factor of, not 3, factor of, yeah, about 3 to 5. So these are 3 to 5 times bigger than the typical galaxy with a similar number of stars. Other galaxies with similar numbers of stars. So there are
Exposure complete.
there are galaxies with lots of stars, very luminous galaxies that can be ultra diffuse, like these things up here, and there are galaxies with sort of average numbers of stars that can be ultra diffuse, and galaxies with low numbers of stars that can be ultra diffuse. Anyway.
Exposure complete.
The object you're looking at on that chart?
So,
yes.
Yeah.
On that chart, one of the objects on that chart.
Yeah, I was wondering where it was.
I wouldn't be able to tell you off the top of my head which one of the dots it is, but
Well, I
something
mean,
like
like, was it towards the larger end or the smaller end, or?
middle, not particularly luminous.
I have a question.
CCD
Yeah,
readout
please.
complete.
When you're trying to measure like the luminosity of these stars, is there a lot of like noise that like it's hard to measure to know if it's actually like a star or something else that could be messing with like whatever you're observing with?
That's a good question, Zayden. The way these galaxies are measured is not brute force. We typically don't just put down a circle and say, what's the light within it? Because there is glow from the Earth's atmosphere, there's background galaxies, foreground stars. So we tend to fit a 2D Gaussian or something like a 2D Gaussian to the light of the galaxy. And instead of actually integrating the pixels on the sky, we integrate over the fit. That makes sense.
Over the, what was that word?
A two-dimensional Gaussian, like a two-dimensional bell curve. Because galaxies, elliptical galaxies look like two-dimensional bell curves on the sky. There are more stars near the center, more stars per unit area near the center, and falls off with increasing radius. So we don't exactly fit 2D Gaussians, but we fit models like that, called Sursich profiles. We fit exponential profiles, where Sursich or exponential describes the function that tells you how much the brightness drops up with increasing radius. Most galaxies, and these are no exception, are brighter near the center than in the periphery. So people have developed functional forms that are good fits to elliptical galaxies. And so we use those kind of functional forms, model two-dimensional functions to fit to the pixel data, and then we integrate over the model. Eric and Sangsun and Elisa are much greater experts in this than I am. So Jim is asking about the difficulties of measuring luminosities of galaxies like these.
Yeah. Especially this kind of faint one is quite difficult one. Yeah, because we cannot see we don't know what's the edge of the galaxies. So we, as Raja explained, we fit the model for that to estimate the total luminosity of that. But if they are faint, we have some errors on the observation. So yeah, so we need to try to fit better. But also, this kind of galaxies usually can explain by some models, but sometimes they have some weird shape or weird feature, weird profile. So in that case, we think about how can we fit that or peculiar features there. Yeah, so that's another difficulty to estimate the accurate flux of the luminosity of these kind of galaxies. Yeah.
What would you say the uncertainty is? It's not, do we know the luminosity to within 10% precision, 20% precision? What is a typical error bar? 0.2 magnitude, 1 magnitude?
Actually, it's very good question. Actually, I want to know about that because it's very faint. It's also very difficult to estimate the error of the right estimation because so we know maybe this kind of faint object, maybe 20%, something like that, mean of the object. We don't know about the exactly what error of this galaxy, but we have some statistics about the mean error. So yeah, if I remember correctly, this faint one has 20% or a little more. Yeah.
Uncertainty.
Yeah.
Yeah. So I think Eric was describing this a few nights ago. This is a nice full circle moment because a few years ago, Eric was a mentor for a program for high school students that we run on the UCSC campus. And the project for a couple of summers in a row, what the high school students had worked on was galaxies like these to try and fit models. And one of the things you have to do is you have to decide what you're going to mask out, bright stars, background galaxies. Do you want to mask them out and fit the rest of the pixels? You want to, so they were doing this kind of model fitting of galaxies with a dual purpose. They were fitting models to galaxies because when you subtract off the light of a galaxy, it's much easier to detect globular clusters, star clusters associated with it, because otherwise they're sitting on some kind of, it's like trying to pick out little peaks from a wildly contoured map is much harder than when you subtract off that contour map. And now all the star clusters are sitting on a more or less flat background. So it was sort of a dual purpose project. One is to measure the luminosity and model the galaxy and subtract it off. The second purpose was to do a better job of measuring star clusters that are associated with the galaxy. So this was a project, I think it was 2 summers in a row in this program that we run at Santa Cruz called the Science Internship Program. So there were high school students working on this. Now we've had modern high school students in this program, but they were not on this particular project. There were, I remember there were students from other schools. One of them continued to work with us during the school year and made a lot of progress. So this is one of those projects that was very, Eric was able to train a bunch of students to do this, and then it was a nice way of crowdsourcing the work. And Gautam, who's joined from India, is an undergraduate student. Gautam, take a moment to introduce yourself, please.
Hi, I'm Gautam. I study in Delhi in India. Yeah, I'm going to be working on the Rajasthan this summer for around 2 months. Hello. Yeah. Should I talk about my project as well?
Please mention your project in a few words.
Yeah, so I mean, essentially my project is just like studying the dynamics of the triangulum galaxy, the dynamically hot component to be specific. So,
and you'll be using data taken with Keck, but with a different spectrograph with DEIMOS, and looking at individual stars and how they move. And Gautam will be a mentor for the SIP program. There'll be 3 high school students working with him. Eric, I was trying to remember, there were 2 years in a row, it was a SIP project, right? To measure, to fit models to some of these to some of the dwarf galaxies, subtract them off, measure globular clusters in them, count globular clusters in them, but also get good models and luminosities and shapes.
That's right. It was it was generically for low luminosity galaxies, but mostly we were working with more normal dwarf galaxies, not the UDGs.
Right. I remember we had a student from the Harker School. We had another student who worked during the fall and continued with this project for a while. There was one student I remember who was just like fantastic. He was it Justin? DU was his last name.
Yes, that's right. You're correct.
He was very good. Right, I'll go back to sharing my screen.
What telescope do you use to get this luminosity data?
That is from the Canada, France, Hawaii telescope, which is on Mauna Kea. But it's an older and smaller telescope, but it's quite powerful for imaging because it has a very large wide field camera on it, and it gets very good image quality being up on Mauna Kea. So it's a different kind of instrument telescope combination.
I figured it would be. How, like on the sensor, about how many pixels across does this galaxy appear? Is it dozens or hundreds?
Oh, okay. So I think with the pixel scale we have, it's about 0.187. So arc seconds, 1 arc second. So each, I'm trying to remember the conversion. Each arc second's 80. Off
I'm
the
just
top
kind
of
of
my
wondering
head,
order of magnitude.
it's order of magnitude. It's about 100-ish pixels across, and the field of view of one of these cameras' images is 20,000 pixels. So, it's you could
on the side, right?
On a side, yeah, 20,000 by 20,000.
So when you're talking about the radius and the Gaussian fit, you've got 100 by 100 pixels approximately to work with.
That's
but we've got plenty of non-galaxy pixels around to fit a baseline.
Exposure complete.
Yeah, this imager is a patch of sky that's big enough to fit in 4 full moons. 1 degree by 1 degree imager, and these galaxies
complete.
are much well. These galaxies are what, about an
No, we're not moving this. We're doing another sky at the same position. Yeah.
But we're waiting for the red readout.
Yeah, and the blue readout.
Okay. You can definitely see continuum on the blue.
DCD readout
But this
complete.
was a sky frame we're seeing?
This is a sky frame, yeah.
DCD readout complete.
We're doing 2 consecutive skies.
Okay. There we go. Started. And Aishani and Zayden, since you haven't seen this before, this spectrograph, the Rob is giant. Okay. What happens is light from the telescope enters through this. That's why we're not seeing any light here. The spot looks black here because the light, instead of reflecting back into a camera, this light is going into the spectrograph, this dark patch here. So light goes into a spectrograph. One of the first things that happens is it gets split up into red light and blue light. So anything that's longer wavelength than green light goes into one part of the spectrograph. Anything that's sort of violet, indigo, blue goes into another part of the spectrograph. And those are these 2 halves. So this is the short wavelength half, the violet, indigo, blue light, and this is the sort of the green, yellow, orange, red light. The green, orange, yellow, green, orange, red light goes into this other half of the spectrograph, and we split the rainbow into 2 parts. The astronomical light rainbow gets split into 2 parts. And so we're taking an exposure here. We're actually taking 4 exposures here, each of length 2 minutes. Each of length 174 seconds, so nearly 3 minutes. And 3 exposures, right? Not 4, 3 exposures of length 3 minutes. And then that's on the red side. On the blue side, we're taking a single exposure of length 10 minutes, 600 seconds that you can see up there. And these vertical spikes that you see here are caused by glow from the Earth's atmosphere. Because we're using a ground-based telescope, so we have to look past the Earth's atmosphere into space, but the Earth's atmosphere glows, and that's what these vertical lines are. Gautam, have you joined a Shadow the Scientist session before, or is this your first one?
This is my first one.
Okay. Welcome, Rob.
Exposure Exposure complete.
Thanks. We celebrated our anniversary yesterday, and so I'm a little late today.
Yeah, congratulations. How many years has it been?
37.
Wow.
Nice.
Same for us. It's going to be 37 this year.
Cool.
I remember this by adding 10 to our daughter's age.
DCD readout complete.
So, Rob, we have a couple of people you haven't met before. Gautam is an undergraduate student in New Delhi, in India, who's going to be traveling to Santa Cruz this summer to work on a research project at UCSC. So we have a program, we partner with a few other institutions. It's called the International Summer Research Program. We actually have a student from Korea coming as well to join our research group, so two of them. And they will both be mentoring high school students when they work on these research projects.
Oh, nice.
Min Cheng, you may have met before, is at Peking University. He's a new member of our research team. Ashani is joined from India, a high school student in India, and Zayden is an undergraduate student at UCSC who's also just joined our research group, my research group in Santa Cruz. He's working not on Virgo cluster galaxies, but a different kind of unusual galaxy called M32. Unusual in the opposite sense. Instead of being too large for its luminosity, there are galaxies that are too small for their luminosity, they're too compact. And Zayden's project is going to be trying to unpack one such galaxy called M32. It's a companion of Andromeda.
Right, recognize it. Cool.
Bright object, right? It's visible quite easily. Visible to the naked eye, right?
31 is, I don't know if 32.
31's bulges, but I think M32's nucleus is quite bright. I should look up its magnitude. So I'm a little intrigued by the fact that in this blue spectrum here, I was able to see continuum before, but now I'm not. Is that because the seeing has gotten worse?
Exposure complete.
I don't think seeing has changed all that much, but we are guiding on that same oblong thing again.
Okay.
I think it's probably because we are on the sky position.
I thought the sky had something in it, right?
It had one thing. The galaxy position had many more.
Had many more, okay.
Yeah. If you look really careful, this is the one
DCD
that
readout complete.
in the sky.
Oh, thanks, Rob. That isn't visible to the naked eye, 8.1. That's too faint. M32's apparent magnitude is 8.1. Would that be visible with binoculars, like powerful binoculars? I don't have a sense of.
I think it would be.
Yeah.
If you had a good sight and a good night.
But we are doing these the 1.5 to 2 hour exposures with Keck and Deimos on individual stars in M32, and sometimes we put slits close to the nucleus of M32. We get this booming signal. That's what Zayden is going to try and analyze.